Hey guys, welcome. So in this video we're going to look at all of the examples that you're going to need for the fundamental theorem of calculus, and we're going to look at these examples big picture. And I didn't plan examples ahead of time because the fundamental theorem of calculus and I are like close friends, and I actually introduced him or her to you in the past, that's to say in a previous video where I show you 4 different proofs of the fundamental theorem of calculus. Kind of like quirky. I was afraid that I was going to say 4 and then stick out 3 fingers, but I made it. And also just before setting up to record this, I saw like one fly going by, and yes, great. So now all you're gonna pay attention to is spot the fly, right? Not the lesson. But yeah, like New York City, you know, it's very diverse. Got rats, like flies, and people. But let's start. Okay. So the fundamental theorem of calculus basically is the fella that says that like the derivative of the integral is just the guy. Now, as I said, I have already in a previous video showed you 4 different proofs, so I can, you know, like casually talk about it here because, well, watch the proofs if you really want to understand it, and each proof is very different from the other, so it's really neat seeing how all 4 of them get to the same place. But yeah, what they show is that this here is equal to that. Now, this is again a little casual because some things are important, which is this limit and this limit may be functions, including a constant function. So this limit may be a and this limit may be x. In fact, the first case that we're going to look at is exactly this, where you have a constant here and just an x there. Now, this function has to be of a different variable than x. So this function here cannot be f of x. It can be f of whatever other letter you want. So let's say t, as it is typical in lots of books. And so then what it spits out, this f here, still an f, but it's of x. So a bit less casual is this, right? This is a statement of the fundamental theorem of calculus, which, as I said, basically says the derivative of the integral is basically a cancellation effect, and so you get the guy that was inside the integral back, like as if they cancel, just like, you know, 2x divided by 2, the 2's cancel, just like that, kind of. Yeah, okay. And again, watch the proof, so if you want to know why this has got to be true. But the most basic case of the fundamental theorem is stated in exactly this way. And so I'll give you an example of this, and the slightly more sophisticated versions are like this one. There are 2 other versions I would claim, and so one of them says this. Again, this here and this here are functions, and so, like, you know, g of x may be something sophisticated like x cubed or sine, right? But remember, a constant is also a function, so I'm fine in just saying that these guys have to be functions, right? Because this constant is a function, right? And so is like g of x equals x. That's like y equals x, right? Okay. So this second, slightly more sophisticated fella says, and I guess, as I said, this just has to be different from whatever letter this is, so we can get fancy and, like, you know, this, make this g of t, and now I could say this is f of v dv, like, just, you know, making very clear the relationship between this variable and this variable, which is that they must be different from one another. Yeah, okay. All right. And of course now it also means that this is, instead of ddx, it's ddt. And what we would say here, again, if it's easier for you to consume with this being an x instead of a t and this being the t, then rewrite it that way and work it out for yourself. But what I did should be just fine. And so I'm going to state this version. And so it would be f of g of t times the derivative of g of t, which is g prime of t. So this here will equal that. So this is a second version, if you want to call it a second version. So first version and second version. And notice that if you had this situation, which is like, you know, this was the constant and this was the function, then you could just swap the limits of integration, which is put the g of t here and put the constant down here, and just compensate for swapping them with a negative sign in front of the integral. So what I'm saying is, like, this here, this second case, if you want to call it a second case, captures also the situation where you have a function here, a sophisticated function here, and a constant there, because you could just swap them by putting a negative in front of the integral. So yeah, that's that. So then the third case, I want to also fit it in here. I'll write real small, like you can see it on your computer though, so we're fine. So the third case will be this slide. D dx, and then h of x to g of x. So that's like when you have a sophisticated function here and a sophisticated function here, of f of t dt. And what this turns out to be is it's going to equal, man, did I pick too small a spot for this? It's going to be f of, but we'll be fine. It's going to be f of g of x times g prime of x, and then minus f of h of x times h prime. I'll just write it like that. Obviously, h prime of x, right? So this third situation is this. Man, I feel like normally like I'd be really upset that I'm like doing it this sloppy, but like I think this is fine, right? Okay. Contemplate. No. Let's move on. So all I have left to do is give you concrete examples of each, and we're good, right? Okay, so the first one, that's simple. So like this is like, say you're given d dx of like, you know, like 0 or like 5 to like x of sine t dt. Let's get fancier. Sine of root t dt. Well, fine. Look at this. What it says is, since this is f of t, you get f of x. So the answer to this, simple. Sine of root x. Done. Okay, so that's number one. So, all right, let's go on to number two, right? Number two says, yeah, so that's when you have a sophisticated function there. So like for that, let's look at this example. D dx of like, let's say like 0 to, or like 1 to, and then let's say e to the square root of x. That's getting too fancy, and then I'm just like making crazy functions because like I can, why not, right? Like 1 plus tan inverse, because this is not hard. That's also what I'm trying to illustrate. Like maybe like, I don't know why, like kids find it intimidating. I really don't get why though, because it's not hard. Okay, and if you watch the proofs, you'll really appreciate it. Okay. I'm not trying to get you to just watch that video. Like I care kind of, but I don't care enough to have repeated myself as much as I did. It's out of the genuine love to share like the joy and love of math. Okay. So look at what it says. So what we're gonna do is say that this is equal to, it's equal to 1 plus tan inverse of, and then e to the root x, right? And then times the derivative of e to the root x, which is e to the root x, times, what's the derivative of root x? 1 over 2 root x, right? I am confident the derivative of root x is 1 over 2 root x. Yeah, so this is it. Okay, so last one, right? Last one is, and before the last one, I want to show you what I was talking about as far as like if the sophisticated function is here and the constant is there. This is what I'm saying. So like if you're given d dx of like 2 and then sine x and then cos y dy, right? Then what you're going to do is first swap the position of these two, and you can do that by writing a negative right here in front of the integral, because it's really saying the derivative of the integral, so it's like that, right? So you put a negative sign right there, and that's going to allow me to put a 2 here and a sine x there, and then you deal with it in the manner you would deal with, it's dictated by that. Right? Okay. Which, if you just want to see it, is going to be negative cosine of sine of x times cosine of x. Right? Okay. So, I don't think I actually need to give you final example for the third type, but I'll do it because I'm nice. So, like, I don't know, tan x, right? And then I don't know, 1 over x, and then let's say, who goes in here? What function do we like? I don't know. It could be like whatever. That's why like I'm like kind of stalling. E to the minus t plus e to the t over 2. Okay, and then dt, right? Okay, so what are we going to do here? We're going to say that this is equal to e to the minus 1 over x plus e to the 1 over x, and then o over 2, right? And then this times the derivative of 1 over x, which is negative 1 over x squared, and then minus, right, the rest of it I'll write over here in the interest of space, and that's going to be e to the minus tan x plus e to the tan x o over 2, and then times the derivative of tan x, which is sec squared x. Alright, I intentionally kind of gave you a complicated third example, complicated looking, just to show you that it's not hard. But otherwise, yeah, I hope you enjoyed this and keep watching. Take care.